Welcome to this video from Derby Physics Tuition, and I'm working with a student studying A-level physics. She's in year 13 studying simple harmonic motion at the moment, and this is a lovely extension question. It's from the University of Oxford Physics Aptitude Test, past papers, drawing on knowledge obviously from simple harmonic motion and from physics that you may have studied in year 12. So a really good extension question to test your understanding of simple harmonic motion. So let's have a look at the question. We've got a mass M is attached to a spring S as sketched in figure A below, and it oscillates with a period T. What would be the period of oscillation of two springs connected in series, which is figure B, and in parallel figure C? And the final part of this question, what would be the period of the oscillations in case A on a planet with surface gravity 2g? Okay, so what we need to do first is derive an expression for the period of a single spring, this spring here, on its own, and then use that to work out the period of oscillation of the two springs when they are attached in series and in parallel. Now, the way we can do that to derive this equation for the period of a spring is that the period is given by 1 over frequency, and frequency is 1 over the period, just rearranging that. Now, the acceleration of this single spring is given by this equation here that you would have met through your study of simple harmonic motion. So the acceleration of the spring is minus 2 pi f squared x. And what we're going to do is substitute 1 over t for f. So we've got an expression for f here. So this equation now becomes okay. Now what we can also say that the restoring force on this spring, trying to restore it back to its equilibrium position, can be given by F equals minus kx, and k is the spring constant and x is the displacement. Now we can also say that that restoring force can be calculated by ma. So if we just rearrange that, if we put these two terms equal to each other, because they both give us the restoring force, then the acceleration will be given by minus kx over m. Now we've got two expressions for acceleration, expression 1 here and expression 2 there. So we're just going to put them equal to each other. Okay, and we can cancel out the x's, and I want to get an expression for the period, so I'm going to square root both sides, so I end up here 2 pi over t, get rid of the minus signs as well, they will cancel, equals the square root of k over m, and rearranging that to make t the subject, we get t equals 2 pi root m over k. Now you might remember that equation. That is the equation you would have used for one of the endorsed practicals, which gives you the period of a single spring And what we can also say from this equation is that the period is proportional to 1 over the spring constant. Okay, so I'm going to write that over here because that's going to help us in the next part of this part of the question here. So that we're being asked what would be the period of oscillation if two springs are connected in series. Now, when they're connected in series, they're easier to extend, and if they're two identical springs, then the spring constant would be halved. So our spring constant for B would be K over 2. So if we've got in B our spring constant is K over 2, what difference would that make to the period? So we're going to put our new spring constant into the equation. T is proportional to 1 over the square root of K over 2. Okay, and if we tidy that up, then T is proportional to root 2 times 1 over K. So what that is now telling us is that when we have two springs in series, the period would increase by a factor of root 2, and that's what we're being asked to prove for the first part of the question. Now, what would it be in parallel? So when you have two springs in parallel, the spring constant becomes 2K. Okay, it becomes harder to extend, so the spring constant is 2K. So if we put that into our equation, T is proportional to 1 over the square root of 2K, and just rewriting that slightly. Okay, now we can see that what's happened there is that the period would change by a factor of 1 over root 2. So what that means is that our period is going to reduce by a factor of 1 over root 2. So when they are in series, the period will increase by a factor of root 2, but when they are in parallel, the period will decrease by a factor of 1 over root 2. So a really nice question there, using physics from year 13 and year 12 to derive the equation for the period of a spring, which is T equals 2 pi root M over K. And that takes us nicely to the final bit, which says what would be the period of the oscillations in case A on a planet with surface gravity 2g. Well, if we look at our equation that we derived for the period of a spring, the period only depends on the mass that is oscillating and the spring constant of the spring. There is no mention of G, the gravitational field strength, anywhere in that equation. So if we move this system to another planet, it would still have the same period of oscillation. Okay, so that's the whole question, the solution to the whole question. Really interesting question, and really broadening and deepening your knowledge of simple harmonic motion. And if you do have any comments or questions, please leave them in the comments section below. Thank you very much.